All right, so today I'm going to talk about chapter 5. Chapter 5 actually has a ton in it. So if you could go back to Intro Chem and remember there was a module all about double displacement, single displacement reactions. So we've got that in this chapter. And then on top of that, we've got the molarity solutions chapter. So we've got two pretty robust chapters in one with chapter 5. So when you open up the chapter 5 folder, that's actually the first thing I write in there. I was like, there's a ton of information here. Now, the good thing is that a lot of it is going to be a review from intro, but there's still a lot of content. And what I did for this one is I pulled in all of my videos from intro chem. You know, double displacement reactions are the same in chem 1 as they were in intro, how to do those. So there's plenty of videos on double displacement reactions, single displacement reactions. Then there's another sort of section or heading where I have solution stoichiometry videos, titration stoichiometry videos. There's a lot there. I'll just put it that way. So the other thing I posted for this module, I have done this in the past. I've put some worksheets in, but for this one, there's quite a few. There's this one that I'm looking at here, which is about solutions. This is going to help us with quiz 5A. Then we're going to look at ionic equations and titration. That'll help us with quiz 5B. And then hoping we have time, we'll get to the redox worksheet, which will help us for 5C. All right. And then, of course, after you do all of your practice quizzes, there's the credit quiz, and it'll be due Tuesday at 11:59 p.m. So you do have a week to work through everything. But like I said, there is just a lot of content there. So definitely get started. I think practicing the worksheets would be good. I also obviously I always make the videos for the chapter notes, go through that as well. All the extra videos might be helpful. Depends on, you know, how you did with intro and how well you remember what you did. But there's certainly a lot there to keep you busy over the next week. And of course, reach out if you have any questions for me. All right, but this first video, or the first worksheet that I'm looking at is the solutions chapter. And forgive me, because solutions used to be covered in chapter 4 in the previous textbook. But essentially what we're looking at in this first worksheet is molarity. And molarity in terms of a concentration term is the chemist's favorite because it's got moles in it. So there are other concentration terms, mass percent, volume percent. We'll get into those when we get into colligative properties later in the semester. But for now, we're going to stick with molarity. And molarity, which you probably remember seeing, is abbreviated with a capital M. And it stands for the moles of solute per liter of solution. And the solution is obviously the entire makeup. It's the homogeneous mixture. And when we did equation writing back in intro, we probably remember seeing things marked as AQ, which means that whatever that was marked AQ was dissolved in aqua or water. And that notes that it's a solution, an aqueous solution. So just as an example, if I had a sodium chloride aqueous solution, the salt, the sodium chloride, and the water together makes up the solution, but the sodium chloride itself is the solute. And the solute has, it's going to be present in lesser quantity, right? And for us, we're not too worried about what, you know, recognizing the solute versus the solvent. For now, we're still sticking with aqueous solutions. So if it is an aqueous solution, right, that means that water is the solvent. All right, and so that should probably seem pretty familiar from intro. Now, like I said, we will get into other types of solutions later in the semester. It doesn't always have to be water as the solvent. And when we get there, we'll talk about, well, the solvent is whatever's present in greater quantity, right? That's usually how we define it. The other formula we're going to look at is M1V1 equals M2V2. This is our dilution formula, and it's initial molarity times the volume equals the final molarity times the volume. And this formula is great when it says something like, you take 10 mils of a concentrated 12 molar hydrochloric acid and you dilute it down to 500 mils. What's the new molarity, right? And so we know as we dilute something, the concentration lowers, right? If you add water solvent, the moles doesn't change, but of course, what it's dispersed in has changed. So your concentration goes down. So in this first question, and I'm just picking up a couple of questions from each of the worksheets, and then I will do the rest of this as my homework for today and scan and post that tomorrow as an answer key. But for now, I'm just going to do a few examples here or there. The first question says, to find the molarity of the solution, And this solution is made by putting 125 grams of sodium sulfate, Na2SO4, into 1,750 milliliters of solution. And if we're going to be solving for molarity, it froze again. Then what I need to do is think about the formula, right? If I'm trying to solve for molarity, molarity is going to be the moles of the solute. In this case, that's the sodium sulfate per liter of solution, an SOLN abbreviation for solution. Now, I don't have moles of sodium sulfate. I have grams, but that's an easy fix. We learned molar mass. That'll help us there. So what I do is I go ahead and put whatever quantity of solute that I was given, I put that in the numerator. And then whatever quantity of the solution, even though it's milliliters, I go ahead and put that in the denominator. And then I just recognize that in my first conversion step here, I'm going to have to convert grams to moles for the sodium sulfate. And as we just talked about, it's got to be molar mass. So I'm going to take the 22.99 for sodium twice, then the sulfur 32.07, and then the 4 oxygens would be 64. So I get 142.05. And of course, again, that's the molar mass or molecular weight of the sodium sulfate. And I've now converted my grams of sodium sulfate to moles. So now in the numerator, I do have my moles of solute, which is what I need in my numerator. Now, the other thing I want to check really quick is that my volume unit for molarity, it has to be moles per liter. And since this is milliliters, I'm going to need another conversion step. All right, so if I sort of ignore, normally with dimensional analysis, we like to cancel as we go. So we're thinking, oh, we'll cancel moles. We don't want to cancel moles. That's what we want in the numerator. So that stays. So now I'm going to sort of just cover this really quick and pretend it's not there. And now I'm going to deal with the milliliters, right? Milliliters in the denominator cancels out with milliliters in the numerator. And liters will go in the denominator, which is what I'm looking for because that's how molarity is defined. And again, we talked about this for chapter 1. If you want to put 1 milliliter is 10 to the negative third liters, that works. Or like intro, we did 1,000 milliliters in a liter, which also works, right? Same thing. So on my calculator, I'm just going to take the 125. I'm going to divide it by 1750. I'm going to divide it by 142.05. And then I'm going to multiply it by 1,000. And it looks like my mass given to me had 3 significant figures. The volume also is only 3 significant figures because there's no decimal to mark that 0 as a sig fig. So after rounding, I get 0.503 molar, capital M. And that would be my concentration of the sodium sulfate. So what we did is we said, okay, if I have 125 grams in 1750 milliliters, what our calculations tell us is that means we had 0.503 moles of sodium sulfate per liter. All right, so that would be a concentration term that we could use for stoichiometry, which is going to come up in just a little bit. All right, so when you're finding molarity, you really have to think about the formula. We need to know how many moles of solute we have. If we're given grams, we're just going to convert that to moles using molar mass. And we need to divide that by the volume of the solution, but in liters. And since we were given milliliters, we've got to change that unit to liters. And so at the end, we can leave it as 0.503 mole per liter sodium sulfate, or we can abbreviate instead of mole per liter, we can just put capital M. All right, so the next question there, B, is pretty much exactly the same. The only difference here is it's a different solute, so a different molar mass. And the volume is already in liters in this case, so we won't need that conversion, the unit conversion at the end for milliliters and liters. But otherwise, that one will work the same way. Now, number 2 is a little bit different. Now what we're going to look at is it says how many grams of the solute would be needed to make this solution. So I need 175.0 milliliters of a 0.25 molar sodium hydroxide solution. And again, the question is how many grams of the solute, which in this case is the sodium hydroxide. So this is a calculation I used to do all the time when I would prep for intro chem and I would make all the solutions back in when I worked on the Gibbs campus. You have a target molarity of the solution that I need to make for my lab. I need this volume for all of my students to use, but sodium hydroxide, when you order it, it's a solid. It comes, as a solid, and you measure the mass that you use. So my question is, how much mass of sodium hydroxide should I put into this 175 mils to end up with a concentration that's 0.25 moles per liter? So what I always like to do with molarity, personal preference, is I like to say, okay, molarity, if I rewrite this, it's basically 0.25 moles of sodium hydroxide, moles of solute, per liter of solution, right? And that per, right, the slash, that's an equivalence line. So to me, this looks like 1,000 grams in a kilogram. It's a conversion factor. So you probably remember from intro, I used to always say molarity, this is going to always act as your conversion step. It is our bridge between volume and moles. And when we do dimensional analysis, I like to always start with a single unit measurement. And that means a mass or a volume, typically. Those are the two. So I'm going to start with my volume, the 175 milliliters, and then convert to moles first. It is the chemist's center point. Everything goes through moles. And then from there, we can take it to grams, again, using molar mass. So another kind of pullback from the last chapter before, anytime you're looking for grams of something, you're going to need the molar mass. So we're going to have to go to the periodic table and get the molar mass of sodium hydroxide. So a little flow chart here. I like, again, to start with volume. We always go to moles first, and then from there, we can take it to mass. All right, so I'm going to start with my 175.0 milliliters of solution. And don't feel that you have to write solution. All right, I know I'm canceling out milliliters. And as I talked about, we would like to go to moles, right? Because that's always the center point. Now, I have to be a little bit careful here. The molarity is 0.25 moles per liter, right? But I want milliliters on the bottom to cancel out. So what I do to kind of shorten this a little bit is I say, well, how many milliliters are in a liter, right? A liter is the same as 1,000 milliliters. So now instead of having to write, two conversion steps, I just took care of two things at once. All right, so milliliters on the bottom to cancel out. Molarity, though, is moles per liter. It's just in the denominator, I'm going to put 1,000 milliliters instead of 1 liter because those are equivalent. So I've canceled out milliliters. I got to moles of sodium hydroxide. Now in this next conversion step, I need to get rid of moles of sodium hydroxide and take it to mass. And again, that's going to come from my periodic table. We're familiar with that one. 22.99 for sodium, 16.00 for oxygen, 1.01 for hydrogen. It's right at 40.00. So 175 milliliters times 0.25 divide by 1,000 and then multiply that by 40. Now with significant figures here, this is another place where you have to be just a little bit careful. Normally when we do dimensional analysis, we go back and we look at the starting measurement. And that'll determine our sig figs. The 175.0 in this case has 4 significant figures. So we might be tempted to leave our answer in 4 significant figures. Now, when we were looking at, 1,000 grams in a kilogram, those are exact values. So they don't limit the significant figures for the answer. They're not measured, right? They're exact values. Molarity, however, that acts like a measurement, right? When we made that solution, we could be really precise about the molarity, or maybe we couldn't be that precise. So the molarity does act like a measured value that way. So I need to look at the sig figs for the molarity. And 0.25 only has 2 significant figures. So that means my answer here at the end is going to be limited to only 2 significant figures. So the calculator gave me 1.75. I just want to type it in really quick one more time, make sure I entered it in correctly. Yep, and so 1.75, I'm going to round that up to 1.8 grams of sodium hydroxide. All right, so that would be the mass of sodium hydroxide I would need. And I would take that mass, dissolve it in that 175 milliliters, right? And that would give me a molarity or a concentration of 0.25 moles per liter. All right, so when molarity is given to you in the question, you want to envision that as your conversion factor. And then if you have a mass or a volume, that's going to be your starting point. Molarity is your bridge between volume and moles, just like molar mass is your bridge between mass and moles. So molarity is really important, obviously, for solutions. So I want to try another one similar to that. Sorry, I didn't mean to move it so quickly. This is the third one on the worksheet. It says how many milliliters of a 0.750 molar H3PO4, phosphoric acid, would contain 35.5 grams of H3PO4. All right, so just like we were talking about, this question is almost like the opposite of what we just did. We started with volume, we went to mass. In this one, we're going to start with mass and go to volume. But again, what I hope will become very familiar, if it's not already, is that when you are given the molarity, it is always going to act as your conversion factor. And the mass or the volume is always going to be what you start with. So in the last example, we had volume to start with. In this one, we have mass. And as I mentioned before, if you have mass, the very first thing you're going to need is molar mass, because as we, I think, are very familiar with chemistry, the mole is always where you go, right? So we have 35.5 grams of H3PO4. All right, and so what I need to do here is get rid of grams and go to moles of H3PO4. And of course, that's the molar mass from the periodic table. So 3 hydrogens would be 3.03. The phosphorus is 30.97. And then the 4 oxygens would be 64. So we get 98.00. Okay, so again, that's the molar mass from the periodic table. All right, and now in my next conversion, I need something that can get rid of moles of H3PO4 and go to volume, but specifically milliliters, because that's what the question was looking for. And again, that's our new conversion for chapter 5. If we're going between, again, mass and moles, molar mass, that looks familiar. But if we're doing volume and moles, then that's where molarity comes in. All right, so molarity will be given to you. It's not something you have to go to the table to find. Molarity will be given in the question. And the molarity, the 0.750, is the number of moles. So that'll go where moles goes on in the bottom on this case. So 0.750 moles of phosphoric acid. And again, that would be per 1 liter technically. But what we can do is, since we want milliliters, like we did in the last example, is substitute 1,000 milliliters for a liter, since those are the same. So I'm going to take my 35.5, divide by 98, multiply by 1,000, and then divide by 0.750. And when I check my significant figures, my mass measurement at the beginning had 3 significant figures. My molarity term also had 3 significant figures. And so what I end up here to 3 significant figures is 483 milliliters. And I just like to type things in twice because you never know. All right. Yeah, 483 milliliters would be needed. So what we just calculated is, if I had this solution concentration, 0.750 moles per liter, and I wanted to know essentially what volume of that would contain 35.5 grams. So what I first had to do was figure out how many moles that is. 35.5 grams divided by 98, that'll tell me how many moles. And if I know that there's 0.750 moles in every 1,000 liters, that means this number of moles that I want, I would only have to use about half a liter, so 483 milliliters. All right, so for those 2 questions, the important thing to recognize is that we're not doing any kind of stoichiometry. We only have one substance. And so there won't be any kind of mole ratio going on here. There's no reaction. And the other thing to recognize is molarity is your conversion between volume and moles, right? Between moles and volume. So molarity is really important for solutions. And again, it does the job that molar mass did for solids. It gets us to moles using the amount that we start with, which in this case is typically a volume rather than a mass. All right, so on the next page, there's some more examples for us to work through. And so I'll move that up. All right, so this next question says, yeah, I'm skipping number 4 because it's just like number 3. It says, when 125 milliliters of water is added to 275 milliliters of a 0.35 molar sodium hydroxide solution, what is the new molarity? All right, so what's happening here is, if we're adding water, then we know that this is dilution, right? We're not doing any kind of chemical reaction. We're just adding more solvent. And what we talked about at the beginning is, if we're adding the solvent and we're diluting it, the concentration is going to decrease. And that's what we're looking for. We want to know what the new molarity will be. So for dilution, you have a nice, easy formula to use. It's always nice when you have a formula. It's M1V1 equals M2V2. The problem with this formula is it's very nice and simple, but students love to use it for stoichiometry. And you can't always do that. And I usually like absolutes, so I just prefer to say don't do it. Don't do it. If there's two substances reacting, then don't use that M1V1, M2V2 formula. That formula only works when you're doing dilution, which means you're not doing any kind of chemical reaction. You just have this sodium hydroxide solution. You're adding water to it. What's the new concentration? That's where that M1V1 formula works out great. Okay, so here's the first thing. What are my initial conditions, right? So whenever you see this, the volume of that molarity, this is a set, right? Right here, that 275 mils of 0.350 molar, that will be my V1 and my M1, right? So I'm starting out with 0.350 molarity. I've got 275 milliliters of that. I'm obviously looking for M2 because that specifically is what the question says. What is the new molarity? But now we have to talk about V2. So this is a little bit different than the questions I asked in intro. What's happening here for V2 is I'm taking the 275 milliliter solution that I started with, that sample, and I'm adding to that 125 milliliters. What I want to make sure and capture is the total final volume. So I have to add those two together to get a final volume of 400 milliliters. All right, so, and you probably would have caught this. You know that if you're adding water, the concentration should be going down, right? It should be less concentrated because you're diluting it. And if you had plugged in the 125 for V2, you would have ended up with an M2 that was actually higher than M1, and you probably would have been like, wait, that doesn't make sense. So just be a little careful because this is worded a little bit differently than what we did in intro. We're adding 125 mils to this 275 initial sample. So we want to make sure and add those two together to get the total volume for V2. What was the final volume after we mixed? So we diluted it to a final volume of 400 mils. So now I'm ready to, plug and chug. I've got an initial molarity of 0.350 molar. I've got an initial volume of 275 milliliters. M2 is what I'm looking for. Whoops, I don't know why I was going to put another equal sign there. All right, and my V2 is 400 milliliters. So I'm going to divide both sides by the 400 milliliters to solve for M2. All right, so cancel that out over here. I'll put my answer over here where I've got some space. So I'm going to take the 0.35 initial molarity, 0.350, times 275, the initial volume, divide it by the final volume of 400, and I'm going to keep three significant figures since that's what everything has. So I round this up to 0.241 molar for the concentration of the sodium hydroxide after dilution. And as we expected, we added water. So concentration went down, went from 0.35 to 0.241. All right, so dilution is just taking a solution and adding water to it. Concentration is going to go down. M1V1 is the perfect formula for that. Okay. Now, as I mentioned, the M1V1 formula, students love to use it for stoichiometry, and you can't. So here's why it can look like you should be able to. So number 7 says we've got solutions of silver nitrate, AgNO3, and calcium chloride, CaCl2. We mix them together, a white precipitate forms. How many grams of that precipitate would be formed if 125 mils of 0.25 molar silver nitrate is reacted? All right, now in this one, we're taking two different substances and mixing them together. So when you see that, the very first thing that I want you to think about is we're going to need a balanced equation. So we're not ready to do any kind of problem solving just yet, because we're going to take that silver nitrate that we're starting with and convert it to the precipitate. So we're comparing two substances. And of course, the only way to do that is through a balanced chemical equation. All right. So we haven't quite got to double displacement reactions yet. So I'm going to actually come back to this question. All right. But we haven't done double displacement just yet. All right, same thing. If I look down at number 8, it'll be the same thing. I've got 2 different substances here. So first thing I'm going to need to do is get the balanced chemical reaction. All right, now for this one is a little interesting. It says I've got 17.22 milliliters of a 0.423 molar sodium hydroxide. It's reacted with 1.150 grams of monoprotic acid. Monoprotic just means that there's only one hydrogen. If it were diprotic, that would mean that there would be 2 hydrogens, like H2SO4. And what we want to know is what is the molar mass of the acid? Okay, so molar mass, what do we need for molar mass? In order to find molar mass without knowing what the actual acid is, right? We can't go to the periodic table and figure it out. Molar mass is defined as the grams per mole, right? That's how we know molar mass. And what I know at this point is I have 1.150 grams of the acid. The question is, how many moles of that do I have? Well, the only way I'm going to figure out my moles of the acid is by understanding my moles of base. And so what I tell you here is that your concentration, like the moles, the H plus, is going to equal the moles of hydroxide. I shouldn't have said concentration, but moles would be equal. Oh, it's freezing again. So in this balanced equation, right, it's hard to say, okay, what's the balanced equation? Because we don't even know what the acid is. But what we can tell is the sodium hydroxide and the acid, whatever that acid is, it's a 1-to-1 mole ratio. So the idea with that is once I figure out my moles of sodium hydroxide, I will then know my moles of acid because it's monoprotic. There's only one hydrogen. For every one hydrogen, we would react with one hydroxide. So for this one, I'm going to take my volume of sodium hydroxide. Remember, always start with a mass or a volume. The molarity of the sodium hydroxide is my pathway to moles, and it tells me that there are 0.423 moles of sodium hydroxide in a liter, right? Because that's how molarity is defined. But because we want milliliters on the bottom to cancel out, I'm going to substitute 1,000 milliliters instead of a liter. And then as I was mentioning, because it's a monoprotic acid, for every mole of sodium hydroxide, I'm going to have 1 mole of acid, right? Don't know what the acid is, but I know that that mole ratio is 1-to-1. So if I take my 17.22 times 0.423 divide by 1,000, I'm going to get 0.00728 moles of that acid. And now I can plug that in, right, to my molar mass determination. So for molar mass, I have 1.150 grams of the acid. In that sample, I found out there were 0.00728 moles. So if I divide, I'm going to get a molar mass of 158 grams per mole. So that would be my molar mass of whatever this monoprotic acid is. And that's actually very similar to something we're going to do in lab in the coming weeks. So monoprotic, again, just means that there's one hydrogen. I know we haven't really talked about acid-base reactions just yet in this particular video, but you probably remember from intro, for every one hydroxide, you need one hydrogen to make water. Acid-base reactions always make water. And since this is monoprotic, meaning there's only one hydrogen per acid, it's going to be a 1-to-1 mole ratio. All right, and that'll be true also with number 10 on the worksheet. All right, now for the next worksheet I wanted to look at, all right, we're going to actually look at the equation writing part of this. So the next section, that what we did today or so far is all what you need for quiz 5A. Finding molarity, using molarity as a conversion step, and then dilution questions. When you get to quiz 5B, we're going to look at a specific equation writing. And so if you look at the Ionic Equations worksheet, it is a very long worksheet, but I do think all the practice is really helpful. So I'm going to take a look at, it's the 3rd page. The first couple of pages is like just, general information. So I'm going to look at the Ionic Equations worksheet on the 3rd page. And we've got calcium nitrate, CaNO3 2 solution reacting with sodium phosphate solution. So hopefully that looks really familiar. Double displacement, we've got an ionic compound in solution reacting with another ionic compound in solution. And the generic format there, the A and the B, A is the cation, B is the anion, C and D, same thing, C is the cation, D is the anion. So when we go to predict our products, we're not going to put A and C together because two positives obviously don't go together. And we're not going to put B and D together. So the only options are we have to put A with D and we have to put C with B. And in a double displacement reaction, we are looking for either two things to happen. The first thing is that it's an acid-base reaction and we form water. Well, we can see here, remembering nomenclature, we don't have an acid, there's no H in front, and we don't have base, hydroxide. So the other possibility is that one of those two compounds forms what's called an insoluble solid, means it doesn't dissolve. And the fancy word for that is a precipitate. And in order to predict that, we need to know our solubility rules. Now, I personally don't think you have to memorize these. I think the polyatomic ions was enough. So this will be given to you for the test, right? And the solubility rules, these are given in order of importance. Rule 1 always dominates whatever other rule you've got. So salts containing alkali metals like sodium are always soluble. Ammonium, NH4 plus polyatomic ion, no matter what it's with, it's always soluble. Nitrates, almost always soluble. Acetate, C2H3O2, soluble. Chlorate, ClO3 -1, polyatomic ion, soluble. The halogens, chloride, bromide, iodide, also generally soluble, but there's a couple of exceptions here that we have to worry about. Silver, lead-2, mercurous. So if I have lead-2 with chloride, bromide, or iodide, those will be insoluble, right? Silver likes to form a lot of precipitates. So silver is insoluble, but again, not when it's with nitrate. If it's silver nitrate, it dissolves. If it's silver acetate, it's soluble. If it's silver chlorate, it's soluble. But otherwise, silver is typically going to form a precipitate. Sulfates are also mostly soluble, but again, we've got some exceptions. A lot of the group 2 alkaline earth metals, and then we've got lead-2, again, silver. Then hydroxide, it says slightly soluble. What does that mean? That means it doesn't dissolve very well. When we get into Chem 2, we start learning about equilibrium of solubility, that even something that's listed as insoluble dissolves to some extent, just not very much. So slightly soluble, if I saw that, I would put solid. That means it really doesn't dissolve very well. You're going to see it. Except of course hydroxides with group 1 metals, right? Because we learned that up here. Group 1 metals are always soluble. But the alkaline earth metals, the group 2, they're not very soluble. If you're familiar with milk and magnesia, that's magnesium hydroxide. So not very soluble, right? Very white and chalky looking. Sulfides, S-2, insoluble. Carbonates, insoluble. Chromate, phosphates, and fluorides. So we're going to kind of refer back to this as we do this first example for double displacement. Now, in my opinion, when you're doing ionic equations, double displacement, forming a precipitate or acid base, your first job is to inspect the ions, right? To figure out what your ions look like. And calcium as an alkaline earth metal, we know is a +2 charge. The nitrate polyatomic ion is NO3 with a -1 charge. Now that 2 subscript on the nitrate is not part of nitrate, it's a charge balance subscript. So I'm going to ignore that for now. I only need 2 nitrates because I'm balancing calcium, but on the product side, nitrate's going to be with something else. So I may not need that 2 anymore. In the sodium phosphate, I look at the same thing. I've got Na3, but sodium's not a polyatomic. It's just a single element ion. So Na+1. The 3 is here only to balance the phosphate group because phosphate is PO4 -3. So when you inspect your ions, the only ions that have subscripts are polyatomic ions. And those ions that are part of the polyatomic, they are locked in place. You cannot touch them. They can't move. They have to stay right where they are the whole way through. If I took off that 3 on nitrate, it's no longer nitrate, right? It's something else. And that's not okay. In double displacement, these are the ions that are dissolved in solution, right? They're aqueous. They've dissolved in water. So the calcium ions and the nitrate ions, they separate. The sodium separates from the phosphate ions, right? And then when I mix those two solutions together, I'm going to see what happens when sodium meets nitrate and calcium meets phosphate. So if I do the, A with D, it doesn't matter which one I do first, but if I do A with D first, I got calcium and phosphate. So I'm going to do this sort of step by step. Calcium is a +2, phosphates -3. So back in nomenclature, if I asked you what would the formula be, you wouldn't put CaPO4, right? You'd crisscross here. You give me Ca3PO4 2, right? And then the sodium and the nitrate, that would just be +1 -1. That actually cancels out. So we didn't bring over that 3 subscript on the sodium, and we didn't bring over that 2 subscript on the nitrate. And also this calcium, we only had 1 on the reactant side, but we ended up with 3 on the product side. So your charge balance subscripts will change because you're forming new compounds. That makes sense, right? I needed 2 nitrates to balance the +2 of calcium, but since sodium's only +1, I only need 1. All right, so that is like, in my opinion, with double displacement reactions, understanding your ions and which subscripts are just for charge balance and which ones are part of the polyatomic. That's like 80% of getting this right. You have to just recognize that 4 in phosphate won't go anywhere because that's part of phosphate. But I need that 2 now to balance out the charge on the calcium. And calcium has to have a 3. I've got a +6 balancing now with a -6. The sodium nitrate 1 to 1 because it's +1 -1. All right, so I've got my products. I haven't balanced the equation yet, but that's okay. We're not there yet. Now I need to figure out which one of these is the precipitate. Now with sodium, it's a group 1 metal. I never even bother looking with that one. It's always aqueous only because that first rule is easy to remember. Salts containing alkali metals, always soluble. So anytime I see sodium, potassium, lithium, I just put aqueous. Now, the calcium phosphate, most of the rules are about the anions, and it says here phosphates are insoluble. So insoluble means that that's going to be my solid. And again, that fancy word for that is that's the precipitate, the PPT. All right, so I figured out which one's my solid. I don't have a balanced equation just yet. So now that's what I'm going to do next, balanced equation. So for the balancing part, we put a coefficient in front. So I've got calcium nitrate reacting with Na3PO4. On the product side, we've got the Ca3PO4 2. And then we also predicted the NaNO3. All right, no perfect place to do, to start, where you want to go with this. But what I've, learned over my years of doing this is that when you have a precipitate on the product side or any compound really, that you had to have a lot of extra subscripts for charge balance, that's usually where I start in this process of balancing both sides. I needed 3 calciums to make calcium phosphate come together. But on the reactant side, I've only got 1 so far. So I'm going to multiply calcium nitrate by 3. Then I look at the phosphate. I needed 2 phosphate groups to make that come together. But on the reactant side, I only have 1. So I'm going to multiply sodium phosphate by 2. Now that 2 in front also applies to sodium. So 3 subscript times coefficient 2, I've got a total of 6 sodiums. Nitrate subscript of 2 times coefficient of 3, again, 6 nitrates. So 6 sodium, 6 nitrates means a 6 in front of the NaNO3 on the product side. So at that point, I have the balanced molecular equations. Let me go ahead and write out balanced molecular equation. Now with double displacement reactions, we can also write what's called a total ionic equation and a net ionic equation. All right, I have to admit, as a student, didn't love the total ionic equations. It's just a lot of writing. And I was kind of like, it seems redundant because we really just talked about this with the balanced molecular equation. So why are we doing this? But I will say that it is actually more accurate. Here's why the total ionic is more accurate. When calcium nitrate dissolves in water, it really doesn't exist anymore. What exists are calcium ions and nitrate ions. That's what happens when an ionic compound dissolves in water, the ions dissociate, they split apart. Sodium phosphate really doesn't exist anymore once it dissolves in water. It exists as sodium ions and phosphate ions. So the ionic equation is going to express that. Instead of looking at calcium nitrate, it's going to say, okay, well, calcium ions and nitrate ions. So anything that's marked aqueous, we're going to break apart into ions. All right. And the important thing here is that ions have to have their charges. So in my first compound, the calcium nitrate, I have 3 calcium ions, so +2. Then I'm going to show that separate from the nitrate with a plus sign. Now, the nitrate, here's what's fun about that. Any charge balance subscript moves to the front. So again, that 3 subscript within the nitrate is locked in place because that's the polyatomic, but that charge balance subscript of 2 moves to the front. And since there's already a 3 there, I'm going to multiply. So 2 times 3, I've got 6 nitrates. For my next compound, sodium, not a polyatomic. So again, that charge balance subscript moves to the front. 3 times 2, we've got 6 sodiums, and then 2 phosphates, right? And again, even though I was like, oh, so much writing, it really is more accurate, I have to admit, right? The calcium nitrate doesn't exist. Once it dissolves in water, it splits apart, the calcium and the nitrate. The sodium and the phosphate, they dissociate. But again, something I mentioned earlier, but it always is good to repeat this, polyatomic ions don't break apart. Like nitrate stays nitrate, phosphate stays phosphate. So that's what I mean by those subscripts are locked in place. Now, on the product side, we've got our precipitate, and that is the chemical change that we would see if we did this reaction. The calcium and the phosphate, they find each other, right? And they stick together. So the calcium phosphate, the Ca3PO42, we're not going to split that because it doesn't split. That's the change. It forms the insoluble solid. But the sodium nitrate, that stays dissolved. So we would still have 6 sodium ions and 6 nitrate ions floating around in solution. All right. Now, technically, this was the part I always really hated. Technically, all of the ions we would label as aqueous. And I don't know why hate's such a strong word. I shouldn't say that. But we would label aqueous, 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 aqueous. I just thought it was redundant. If it's an ion, obviously it's aqueous. And then the precipitate obviously gets marked as a solid. All right. So total, everything is there. Ionic, we have focused on the ions. Ions have to have charges. The only thing that won't have a charge is the compound. And again, that's the precipitate, right? We don't break up the precipitate. Now, the net ionic, the third and final way to express the exact same reaction. My allergies are bugging me. For net ionic, what we're going to do is just show what makes the solid. And so I kind of always looked at total ionic like a math formula. And if you have like terms on both sides, they're going to cancel out, right? We come into this reaction with 6 sodium ions. When we're done, we still have 6 sodium ions. That says to me, we didn't use any sodium ions, right? So we're going to cancel those out. And the nitrate also didn't get used. So those are called spectator ions. I guess the idea is that they're in the test tube watching the reaction happen. And so we get rid of those. And the net ionic becomes what is the chemical change, which is the 3 calcium ions finding the 2 phosphate ions to make the Ca3PO42 precipitate. All right, so the net is just showing what made the solid. All right, so that's a lot for just one reaction. So if I kind of scroll back up here a little bit, your first job with double displacement is identify your ions. Make sure your charges are correct. Again, this is like 80% of getting it right. When you come over to the product side, you put your A with your D together, crisscross to balance charges, then your C with D together, crisscross if you need to balance charges. If you can't, when you go to this next step, if you can't get the equation to balance no matter what you do, more than likely it's because one of your charges wasn't quite right. So go back and double check those, make sure that they're right, make sure that you crisscross correctly to get the right compound, because the balancing part should be the easy part. All right. 3 calcium. So we put a 3 in front of calcium nitrate, 2 phosphates, so a 2 in front of sodium phosphate. That gave us 6 sodiums and 6 nitrates, so a 6 in front of NaNO3 on the product side. Once you have the balanced equation, you can go and do the total ionic, keep the mass balance, right? We should have a balanced equation here. And then net is just removing what are called the spectator ions. All right, so that is a good example of double displacement. If you feel like you need a little bit more time with that, remember there are a few videos that I posted that are marked double displacement reactions. So there's definitely more examples for you to look at. But the rest of the worksheet also has more for you to practice. There's a lot here. What I'm going to do today is I'm going to make the answer key to this and I'll scan it and post it tomorrow. So you can double check your work against mine and then let me know if you have any questions. But another type of double displacement reaction is when we form acid base makes water. So we don't have to worry about solubility rules for this, but we do want to look at how acid and base come together to make water. So the example I've got here is acetic acid, HC2H3O2 in solution, and sodium hydroxide in solution. And the reason why I chose this one is because with acetic acid, sometimes the H in the middle kind of throws off students with this, but we're always just looking, we've got this H in the acid combining with the hydroxide from the base. And what you want to kind of think about with acid base is for every hydrogen, you need 1 hydroxide to make 1 water. So to me, this was sort of the easy way to approach acid base. So when I look at my acid, I have 1 acidic proton. So that's what was meant by a monoprotic acid. Yes, there are other hydrogens here, but they're not acidic. And when you get into organic chem, you'll see why that is. But for now, we write any acidic hydrogen in the front. So we've got this acidic hydrogen, just monoprotic, 1 there, reacting with 1 hydroxide. So we're going to make 1 water. And some students prefer to write water as HOH because that's really what it looks like, right? We take the H and the OH and we make HOH, and that's fine. And then what we have left is the sodium and the acetate. So in acid-base reactions, I like to sort of approach them this way, but you can do it the double displacement way. The double displacement way, again, is to look at the ions. My cation here is H+. The anion is the acetate polyatomic ion. In my second compound, I've got the sodium ion and I've got the hydroxide anion, OH -1. So again, I don't know why it keeps focusing, but the H+ is our acid, the hydroxide is our base. So when we put A with D, right, we're going to make water. So one of our products here is going to be water. Water is marked L for liquid, not aqueous, because it doesn't dissolve in water, right? Water is water. So aqueous is something that dissolves in water for an ionic compound. So water just gets marked liquid. And then the other compound we would have here is the sodium and the acetate. +1 -1 cancels out. So we would have NaC2H3O2. And that one, we would check our solubility rules. But like we talked about, sodium is always soluble, no matter what. So we put aqueous there. So for this particular reaction, it's actually already done. We'd have our HC2H3O2 reacting with our NaOH. And we would form water. And then the sodium acetate, NaC2H3O2. All right. So everything is 1-to-1 here. So there isn't any extra balancing we have to worry about. I'll spare you the total ionic equation, but I do want to talk about the net ionic equation here really quick. Normally what we focus on with the precipitation reactions is, right, what we talked about was you show what makes the solid. And you would look at this and say, well, I didn't make a solid. So what do you want me to do for net ionic? The aqueous substances do split apart, but the water stays together. So instead of showing what makes the solid, we're showing what makes the water. All right, so most acid-base reactions have the same net ionic equation, which is the hydrogen ion from the acid combines with the hydroxide ion from the base to make water. It doesn't always have to be this way because sometimes the hydroxides are from solids themselves, but this is really the heart of an acid-base reaction. You got your hydrogen, acidic hydrogen from the acid, the hydroxide from your base, they come together, they neutralize, and they make water. So net ionic acid-base reaction typically looks like that. Like for the next example, number 5, that's how it's going to look. We're going to have hydrochloric acid with sodium hydroxide. Again, hydrogen plus hydroxide makes water. All right, so visually, we don't really have a lot to tell us that anything happened here. So a lot of times with acid-base reaction, we'll use pH indicators to show that there's been a change. And you might remember doing that with titration, right? We had the phenolphthalein indicator, and that told us when we had a pH change. So we knew that there was some kind of chemical reaction taking place. All right, so for your second video with, your second quiz, the second practice quiz, so for 5B, we look at double displacement reactions, acid-base reactions, and then we have to get into some stoichiometry. So that is my next worksheet. And when we look at the stoichiometry, we're going to see that molarity again be very important as a conversion factor. Now, what I'm going to do now that we've talked about double displacement is I'm going to go back to number 7 on that very first solutions worksheet that I talked about at the very beginning when we were looking at molarity. And for number 7, what we had was the silver nitrate and the calcium chloride. And what'll be helpful here is that it'll help us review double displacement again, and then also look at the stoichiometry of this. So now we'll go back and do both. So we have solutions of, so that means that the silver nitrate starts out aqueous, and the calcium chloride also starts out aqueous. And we know we form a precipitate here because that tells us we form a precipitate. Now, what I need to do is identify my ions. So I've got my silver +1 combining with the chloride -1, right? Chlorine is not a polyatomic. That 2 subscript is just a charge balance 2 because calcium's +2. So when chlorine comes over, that 2 is not locked in place. It's not polyatomic. So I just look at chlorine by itself, halogen, -1, +1, -1. That's it, silver chloride. Then for the second compound, I've got my calcium, which I know is +2, partnering with nitrate, which is -1. All right, and so here for charge balance, crisscross, I need 1 calcium and I need 2 nitrates to make calcium nitrate come together. Now, when I check my solubility rules, nitrates are soluble, so that's going to be aqueous. And again, kind of referencing this really quick, the chlorides are mostly soluble, but silver was one of the exceptions. So that silver chloride is going to be the precipitate. So when the question says, how many grams of the precipitate are formed, then now I know that that's what we're looking for. We're looking for the mass of the silver chloride. All right, so it was just sort of embedded here. And I've got 125 mils of a 0.25 molar silver nitrate. The calcium chloride isn't mentioned here, so we're going to assume that this is excess. We don't have to worry about limiting reactant problem. And I've got a volume of silver nitrate and a molarity. And like we talked about at the beginning, we always start with a volume. So we have 125 milliliters, and we're starting with silver nitrate. Now, as we talked about, molarity is the conversion factor for solutions, right? That is our way to get to moles. So what we know is there are 0.25 moles of silver nitrate per liter, because again, that's what the molarity gave us. Again, milliliters is what we start with. So we want to go ahead and put 1,000 milliliters on the bottom to cancel that out. Now I've got moles of silver nitrate. Now what's different now is I have a balanced equation. I'm doing a chemical reaction. So my pass through in the middle has to be my mole to mole ratio. So I'm going to get rid of silver nitrate on the bottom, and I'm going to go to silver chloride on top. Now, before we do that, I hadn't balanced the equation yet. I got ahead of myself. So real quick, 2 nitrates needed to balance the calcium. Over on the reactant side, there's only 1 nitrate. So I put a 2 in front of silver nitrate. That 2 meant 2 silvers. So on the product side, 2 in front of the silver chloride. Now my chlorine also has 2, but that balances with the 2 on the reactant side and 1 calcium on both sides. So we have a balanced equation now. In our mole to mole ratio, right? To change substances, the only way to do that is through the mole to mole ratio. In this case, it's 2 to 2 from our balanced equation. And then the last thing is with the silver chloride, we wanted to know mass. So if I want grams, and I'm going from moles to grams, I need the molar mass from the periodic table. So silver is 107.87, chlorine is 35.45. So I get 143.32 for the molar mass of the silver chloride. So what I'm going to do is take my 125 times 0.25, divide by 1,000, times 2 divided by 2 cancels out, and then times 143.32. And again, when I check my significant figures, my starting volume had 3 sig figs, but my molarity only had 2 sig figs. So my answer here can only be 2 significant figures because of the molarity. So it'll be 4.5 grams of the silver chloride. All right, that'll be the mass of precipitate formed, assuming 100% yield, right? We talked about percent yield before. All right, so again, molarity is our conversion for volume of solutions rather than using molar mass when we want grams. So when you read through the question, if it gives you a volume of a solution, the molarity is your conversion factor. It has to be given to you. If you're looking for the mass or you're given the mass, then you know you're going to need molar mass because, of course, that's the only way to get to and from grams. And the center point is always your mole to mole ratio. If you're doing a balanced equation, right? If you're doing a reaction, you need the balanced equation, then you get your mole to mole ratio. All right, so the other thing that's covered on quiz 5B is titration problems. So in the set of worksheets I gave you for chapter 5, there is a worksheet specifically devoted to titration. So I'm going to go and pull that one next. And there are a couple of questions I want to do on this one before we get to redox at the end. So for the acid-base titration worksheet, all right, there are some questions here to keep us busy. Let's see, I may not be able to get, yeah, I'm going to have to go ahead and move all that. There are a couple of questions here. All right, so the first one says, what volume of a 0.250 molar sodium hydroxide is needed to neutralize 22.10 milliliters of a 0.120 molar HCl? So this is the question where a lot of students would want to use M1 V1 equals M2 V2 because it looks like it would just be perfect, right? I've got a molarity, I've got a volume and a molarity, and I need a volume. So doesn't that look like M1 V1 and then V2 M2? The problem though is that I have 2 substances here. So I know that there is a chemical reaction taking place, and what the M1 V1 formula doesn't take into account is it doesn't allow for us to calculate if the mole ratio isn't 1 to 1. Because if you think about it, molarity times volume is moles. So what the formula is saying, your moles 1, right, initial moles is equal to final moles. So this dilution formula really should just be used for dilution. However, it can be used if your mole ratio is 1 to 1. And I always kind of hesitate telling students that because inevitably students will use it for all questions, whether it's 1 to 1 or not. But what I will put, because I've got 2 different problems I'm going to do here. In this first reaction, it is a 1 to 1 mole ratio. All right, so you can use M1 V1 equals M2 V2. All right, I'm going to show you the long way though, but I'll explain why the formula will work. So I'm looking for the volume of NaOH, and I've got 22.10 milliliters of HCl. And remember, those molarities are our conversion steps. So I'm going to start with volume. I've got 22.10 milliliters of HCl. Molarity is going to get me to moles, 0.120 moles of HCl per liter, or in this case, per 1,000 milliliters to cancel out milliliters. All right, now, once I have moles of A, I'm going to go to moles of B using my mole to mole ratio. 1 mole of HCl to 1 mole of NaOH, right? It's this step right here, because my mole ratio is 1 to 1, that I could use the M1V1 formula if I wanted to, right? But I'm going to keep going with this format because this format always works, whether the ratio is 1 to 1 or not. After I've got my moles of sodium hydroxide, now what I need is to get rid of moles of sodium hydroxide and go to volume. And that's where that molarity will come in, right? That's our bridge between moles and volume. So 0.250 moles per liter. It doesn't specify, so I can leave it in liters. If I prefer milliliters, then I can do that too. It really doesn't matter to me. So I'll take the 22.1, multiply by 0.120, divide by 0.25. This way the thousands cancel out. And again, looking at three significant figures, because even though the volume starts out with 4, both of my molarities are only 3 sig figs. So my answer here could only be 3 sig figs. So I'm going to take 10.6 milliliters of my sodium hydroxide and react it with my 22.10 milliliters of HCl. All right. So if you did plug this into M1V1 equals M2V2, M1V1, M2V2 would be the unknown. You would get the same answer. However, in the next question, it's saying we've got this hydrobromic acid with barium hydroxide. And again, it looks like it should work, right? I've got a V1, M1 is what I would be looking for. I've got a V2 and an M2, so it looks like it should work. But the mole ratio in this case of the HBr and the barium hydroxide is not 1:1. All right, so mole ratio is not 1:1. So I can't use M1V1 equals M2V2. All right, so we're going to solve it the same way we did up here, or at least mostly, but we don't want to use the M1V1 formula, all right, because mole ratio is not 1:1. So I've got 25.20 milliliters of HBr. I've got 35.55 milliliters of barium hydroxide. What's different here is I'm looking to figure out the molarity of the HBr, and I'm given the molarity of the barium hydroxide. So these questions are a little bit harder because we're solving for the molarity of HBr. The other thing that makes this harder is I had mentioned you always start with a mass or a volume, and you look at this, you're like, well, wait a minute, I got 2 volumes. So now what do I do, right? What you kind of think about is, okay, I've got a volume of solution, two of them. The only way for me to get to moles, which I know is where I always go first, is I have to have molarity. Well, the 25.20 milliliters, I don't know what the molarity of that is. That's what I'm actually trying to figure out. So I can't start with that because I'd have nowhere to go. The barium hydroxide, however, I've got a volume and I have the molarity. It tells me it's 0.158 molar. So I can start with my 35.55 because I know how many moles will be in that because I know what the molarity is. So I'm going to start with my barium hydroxide. So I start with the 35.55 milliliters, and molarity will get me to moles. So 0.158 moles per 1,000 milliliters. Then I know I need my mole to mole ratio. So this is why M1V1 wouldn't have worked here because my mole ratio is not 1:1. So getting rid of barium hydroxide on the bottom, going to the hydrobromic acid on top, pulling in those coefficients from the balanced equation. All right, so this right here would tell me how many moles. Now, if we followed the last example, once we get to moles, we use molarity to get to volume. This one's different. I want to get molarity. I have volume. So it's basically like I need to figure out what this would be if my answer is 25.20 milliliters. I do these in steps, right? So if a question is asking me what is the molarity, like we talked about at the very beginning of the video, if I'm trying to solve for molarity, I want to think about my formula. I need moles divided by liters. If I stop here just for a quick second, take 35.55, multiply by 0.158, divide by 1,000, and then times that by 2, I get 0.0112 moles of HBr. Right, so now I know how many moles of HBr I have. That many moles were in that 25.20 milliliter sample. So that's going to go into my denominator, right? Now I know I had 0.0112 moles of hydrobromic acid in my 25.20 milliliter sample. So to solve for molarity, I have my number of moles. I've got that present in this volume, the sample that was given to me. And just like we talked about molarity, when you're solving for it, it has to be moles per liter. So we'd have 1,000 milliliters to 1 liter, quick conversion to get the units to cancel out right. So I'll take my 0.0112, divide by 25.2, and then multiply by 1,000. And again, keeping 3 significant figures, I get 0.444 for my molarity of HBr. I'm just going to type it in one more time. Divide by 25.2 times 1,000. Yeah, okay, that's the right answer. So 0.444 concentration molarity of HBr. So when it's a titration question and you're solving for molarity, I like to do it in 2 parts. If you're solving for molarity, part 1 is find the moles of your B, right? Wherever you're headed, right? Your starting material is your A substance, where you're headed is your B substance, right? So find your moles of B. Start with your volume of A, use molarity of A to get to moles, bring in your mole-to-mole ratio, that'll get you to moles of B. Then your second step is to find the molarity of B. All right, and then for that, we need the formula. We take our moles that we just calculated, divide it by the volume of the sample, just make sure the volume unit is in liters, and that'll get you your molarity. So anytime you're asked to find molarity in a stoichiometry setup where you have to go through the mole-to-mole ratio, I do it in 2 steps. I get my moles first, and then I divide it by my volume to get my molarity. All right, so everything for quiz 5B is there. That's a huge amount of material. Double displacement reactions, acid base, solution stoichiometry, titration. That is a ton of material. The third practice quiz it's a big shift. It's now all about redox. It's going to take us back to single displacement reactions, which we just did a little bit of, like a very tiny bit with alkali metals in the last chapter, but we're going to do a little bit more of it now. So there is a Redox Reactions worksheet, and there's a few topics that we will remember, I think, from Intro Chem, single displacement reactions being one of them. But we're going to add to it just a little bit. We're going to talk about oxidation states and what is reduced, what is oxidized, what is the reducing agent, what is the oxidizing agent. So there's a little bit more that we're going to add to from what we did with intro. All right, so for the redox reactions worksheet, first thing that we're going to do in this first section is figure out the oxidation number of whatever is underlined in these compounds or polyatomic ions. So some of these, it's going to look really familiar. If it's an ionic compound, it's just like what we did with nomenclature. So MnCl2, right? If we were naming this, we would say manganese, Roman numeral, what, right? And then chloride. Cl would be called chloride. So to find the oxidation state or the charge on the manganese, that's going to seem very familiar, right? The chloride is -1. There's 2 of them in the compound. That's a -2 total. So to balance, the manganese must be a +2. It froze again. So if I were going to name this, I would say manganese 2 chloride. So the charge on the manganese is +2. In that case, the charge and the oxidation number, they're the same thing, right? So when we were calling it a charge and getting the Roman numeral, now we're calling it an oxidation number, same thing. But in the next compound, I know it's hard to see, it's C2H5OH. This is a covalent compound, right? Just nonmetals. And what we talked about was with covalent, there are no charges. So there are no ions here. So these are not ionic charges anymore. They're called oxidation numbers. So we're going to try to figure out the oxidation number of the carbon. Now, some of these, when you look at how to identify what the charges are, what I always say is when you look at your periodic table, go out and then move in, which I know seems kind of weird, but what we know here is halogens like to be -1. That typically dominates oxygen -2, not always. There's always exceptions. All right. But then over here, we know like the group 1 and hydrogen are always +1. The group 2 are always +2. Remember in the middle, we don't necessarily know what these charges are. Carbon, we didn't always assign a charge for. So when we're looking at the C2H5OH, the hydrogen should be what we expect, +1. The oxygen should be what we expect, -2. It's the carbon that we don't know what that is. All right, so I'm going to say let carbon be X, right? Some integer X, right? So I've got 2 carbons, so 2 times that charge of X, and it froze again. Okay, so 2 times that charge of X, whatever the X charge is for carbon, we don't know the oxidation state. Then with hydrogen, I've got a total of 6, 5 plus 1. So I'd have 6 hydrogens, each with a +1 charge. And then my oxygen, which is a -2 charge. And I have a compound here, so the charge has to overall go to 0. So when I look at this, I have +5 plus 1, so a total of +6 from the hydrogen, a -2 from the oxygen. So +6 -2 means net here is a +4. So to balance, I need a -4. So that X here must be a -2. But what we can do is I'll show you the algebra up here. I'm going to move 2X by itself on the left side. I've got +6 -2, which means +4. If I subtract 4 from both sides, that means a -4 on the right. So basically, +6 -2 means this is a +4. I'll subtract 4 from the left and the right. So 0 minus 4, that gives me a -4. So if 2X is equal to -4, that means my X oxidation state on the carbon is a -2. So what I'm looking at is -2, -2, so -4 total, +5 would get me to a +1 overall, plus another 1 gets me to +2, and then the oxygen is a -2. So that's how everything cancels out and goes to 0. All right, we're going to try another one here. We've got ammonium chloride, NH4Cl. N, I'm going to say is X. Hydrogen is a +1, but there's 4 of them. So 4 times 1 is a +4. Chlorine, we know, is a -1. And overall, we've got to go to 0 because it's a compound. So if I have 4 minus 1, that means a 3. I'm going to subtract 3 from both sides. That means X is a -3. So that oxidation state on the nitrogen would be a -3 charge. Now, in each of those compounds, we end up with going to 0 overall charge because they're compounds, right? The overall charge is 0. But notice here we've got polyatomic ions. We have S4O6 -2. We have C2O4 -2. So I'm going to look at the oxalate here. I've got C2O4 -2, and I'm going to write it over here in the margins so that we can see it a little bit better. All right, again, we're looking for carbon. Carbon is the one we don't know. Start with what we know. We know oxygen's -2. So for carbon, I'm going to say 2 times X, right? Because I don't know what the charge on carbon is. Oxygen is a -2, and I've got 4 of those, so 4 times -2. And overall, I have a -2 charge. We're not canceling and going to 0 here because it's a polyatomic ion. So that is my net charge. So I've got 2X plus a -8 equals -2. So I'm going to add 8 to both sides. So 2X is equal to 6 because the 8's cancel out here. -2 plus 8 gets me to +6 overall. So X here would have to be a +3. So carbon would be +3 in its oxidation state in oxalate. All right, so the oxidation states, it's a little bit different from what we saw with intro. You know, if it's an ionic compound, it looks very similar. But if we're breaking down those covalent compounds, non-metal with non-metal, right, then it starts to look a little odd, I could say. Now, when we get into Chem 2, we're going to do a bunch of this. We've got like 2 or 3 weeks devoted to electrochem, redox oxidation, and looking at all of those oxidation states. So we're going to do a lot more of it. Here, we're just practicing the oxidation numbers. All right. Now, when we get into actual redox reactions, this is going to look similar to single displacement. We'll talk more about that though in just a little bit. I've got a zinc and a copper 2 ion. On the product side, I've got copper and then zinc ion. In single displacement reactions, what happens is very similar to what happens here. Your zinc starts out as neutral. It's by itself. There's no charge indicated, so that means it's got no charge. The copper +2, obviously that is a cation, right? A positive ion. And in single displacement, what happens is the cation becomes the neutral, and the neutral zinc became the cation, the +2. All right. So this is different than double displacement. In double displacement, the ion charges do not change left to right. In redox, however, your charges change. And redox is short for reduction, oxidation. And that's why it's called redox. When something is reduced, electrons are gained. When something is oxidized, electrons are released. Now, what you have to remember is electrons are negative particles, right? So if you're gaining negative particles, your charge goes down. So that is actually how I remembered it. Whatever is reduced, the charge is reduced. To me, that made it very literal, and it was very easy to remember. If something is oxidized, electrons are released, meaning you're releasing your negative. So your charge is going to become more positive. So when I look at this first equation here, the zinc is turning into zinc +2. So what I can see from that is it's going from a 0 charge up to a +2. So that means the charge is going up, and that means that is the oxidation, that is what has been oxidized. So the element here that's been oxidized is the zinc. The zinc has been oxidized. It has lost 2 electrons. And we know that, right? For zinc metal to go to a +2, that means it's lost 2 electrons. So what has been reduced? Well, the cation with a +2 became neutral. So it went from a 2 down to a 0. So in this case, the charge has decreased. So that is the reduction step. So the copper +2 was reduced, right? So when we are identifying what is oxidized and what's reduced, this is always going to be from the reactant side. So we're labeling the species on the reactant side of the equation. So zinc is oxidized because the charge goes up. Copper is reduced because the charge went down. So those are my 2 reactants that I started this equation with. Now, the agents, this is supposed to be oxidizing agent and reducing agent. It's the opposite. To me, I felt like that was the easiest way to remember it. Technically, the oxidizing agent is the substance that is reduced. And I remember when I was learning this, I was like, did they mean to make this confusing? But the idea is whatever is reduced is taking in electrons and is the agent that allows for the other substance to be oxidized. So what you want to remember is the oxidizing agent is whatever it is that's reduced. The reducing agent is whatever it is that was oxidized. So you're just repeating these answers, right? Just the oxidizing agent is what is reduced. So that is the copper 2. The reducing agent is whatever was oxidized. So that is the zinc. All right. So if we try another one here. All right. Now the next one, aluminum goes from neutral to +3. So releasing electrons, that is going to be oxidized. The charge is going up. The iron is being reduced. It's going from a +3 down to a 0. So the iron 3 is reduced. The oxidizing agent is whatever it is that's reduced. And the reducing agent is whatever it is that's oxidized. All right. Now this next one, this is where the oxidation states are going to come in. This is a little bit harder. I've got CH4 methane with oxygen to make carbon dioxide and water. So you recognize that's a combustion reaction. And what I can look at here, and I know it's not balanced, but it's actually okay. It doesn't have to be. Hydrogen we know is a +1. Carbon is the one that we don't know. So if hydrogen is a +1, and there are 4 of them in the compound, that's really a +4. So to balance, the carbon would have to be a -4. So the oxidation state on the carbon is a -4, and the oxidation state on each hydrogen is a +1. Now, oxygen by itself, diatomic, it's not an ion, right? This is the Hofbrinkel, right? That's a neutral. There's no ion. It's not like one of the oxygens is a +2 and the other one's a -2, right? They're both 0. When I come over to carbon dioxide, again, do go look at your periodic table when you're trying to assess what charges to do first. Always do the ends first. So I'm going to do oxygen before carbon, right? Whatever's closest to the ends, I do first. So oxygen, do what we know, -2 when it's in a compound. When it's by itself, it's a 0, but in a compound, -2. There are 2 of them here, so that's really a -4. So the carbon is now a +4. And in the water molecule, hydrogen is a +1, oxygen is a -2. All right, so when I look at this, what substance was oxidized? All right, again, oxidized means that you have lost electrons, you've lost negative particles, so your charge has gone up, right? So -4 up to a +4, that carbon is definitely the one that's oxidized. So the carbon in the CH4 is oxidized. What is reduced? Oxygen went from a 0 to a -2 on the product side. So the oxygen in the O2 is reduced. The charge went down. So again, what is the oxidizing agent? It's whatever is reduced, right? O2. The reducing agent is whatever was oxidized. So that was the carbon in the CH4. All right. So for oxidized and reduced, it's just going to take a little bit of practice, I think, practicing getting your oxidation states and then recognizing that if your charge increases, it goes up, becomes more positive. That means you've lost negative particles. That means oxidation. What I always felt was easier to remember is whatever is reduced reduces its charge. So oxygen goes from a 0 to a -2, obviously reduced, right? And so by default, the other substance is the one that's oxidized. That kind of made it easy for me. That's how I did it. So whatever's reduced reduces its charge. So when we look at oxidizing agent and reducing agent, then just remember it's backwards. Whatever is oxidized is the reducing agent. Whatever is reduced is the oxidizing agent. Because again, if something's reduced, it's taking in electrons. It is the agent that allows the other substance to be oxidized. In a redox reaction, you can't have one without the other. If something's oxidized, something has to be reduced. There has to be an exchange of electrons. That is redox. So rather than looking to see a precipitate form, in redox, we're looking for electron transfer. That is what has to happen in a redox reaction. Now, the last thing to talk about are single displacement reactions. And what I want to look at, I'm going to put this on this like last page over here. We don't need that example. We're going to make up our own. Is when I look at single displacement reaction, I've got this activity series of metals, right? And this is on your solubility rules. So you don't memorize this. This would also be here on your test. The metals on the left, right? These are most active metals. All right. So lithium, potassium, calcium, sodium, you never find these in nature as elements. They are so reactive that they have to be stored in oil, or else they'll react with the oxygen and the little bit of water vapor that's in the air. They are very quick to react. So they have to be stored very carefully. Then you've got metals over on the right, platinum, gold, silver, copper. We're familiar with those. Those are not very reactive. They make great jewelry, right? We can wear them, wash our hands, go to the beach, and they don't disintegrate. That's not the case with a sodium or a calcium metal or even magnesium, right? Those are very reactive. So what you want to remember when you look at the activity series is that the metals on the left prefer to be in their ion form, right? They're preferred to be in compound form as cations. The metals on the right prefer to be in their elemental form by themselves, all of their electrons intact. So if I just take an example here really quick, let's say I take magnesium solid and I put it into a copper 2 chlorate solution. All right, if I compare those two metals, right, this is what makes single displacement. You have a single metal. It's typically going to be solid because we don't get to play with mercury anymore. And then you've got an ionic compound dissolved in water. And what you're looking at for single displacement is, will A and B switch places? All right. And sometimes the answer is no, and you have no reaction. I'll show you that next. So when I look at my activity series of metals again, really quick, magnesium, I can tell is more active than copper. All right. Copper is less active. Magnesium is more active. All right. So what we learned in intro was the less active wants to come out and be by itself, right? So the less active wants to be alone. The more active wants to be playing with the buddy. That's kind of how I thought about it. So when we break this down in a redox way, your element that starts out alone is your neutral. If a reaction occurs, the neutral becomes the cation. So magnesium here becomes +2. I'm going to partner it with the chlorate just for charge balance, which is -1. So I need 2 of those to balance the Mg. Then the copper, which starts out as the cation, in this case +2, will become the neutral. All right, so that is redox, right? I'm changing my charges. I went from magnesium with 0 charge to now magnesium +2. The copper in the copper 2 chlorate starts out as a +2, and now it becomes a neutral. So what is oxidized? What's reduced? Now we can add that terminology. So magnesium goes from a 0 up to a 2. So the magnesium is losing electrons, right? So, come back. Magnesium has lost 2 electrons. And so that shows oxidation, right? Charge has increased. The copper charge is reduced, went from a 2 down to a 0. So it has gained electrons. So that is my reduction. So what element was reduced? The copper 2. What element was oxidized? The magnesium. All right. And to add into that the terms that we had from the worksheet, the copper 2 then is the oxidizing agent, and the magnesium is the reducing agent, right? Whatever's oxidized is the reducing agent. Whatever's reduced is the oxidizing agent. Now, sometimes, as I mentioned, nothing happens, right? So your copper prefers to be reduced. That's what the activity series really tells us. When we look at electrochem and chem 2, the activity series is going to present itself differently. Instead of looking like this, it's going to be listed as reduction potentials. So it's going to be looking at, okay, how bad did these metals like being reduced? So we're kind of getting ready for that. So the metals over on the right really want to be in their reduced form, meaning they want all of the electrons. The metals over on the left side, they prefer to give their electrons away. They're more stable as ions. So the metals on the left, they prefer to be in the compound. The metals on the right, they prefer to be by themselves as the neutral. So if I change this, if I then say, okay, well, how about if we take lead solid and put it into a solution of aluminum chloride? Well, no, chloride's not. Let's do chlorate, because otherwise we're going to start a different discussion. Okay, so I've got lead solid and aluminum chlorate solution. When I look at my series now, here's my lead, here's the aluminum. Aluminum is more active. The lead is less active. The less active prefers to be alone. The more active prefers to be in the compound. Since that is how these already appear, we're going to say no reaction, right? Nothing occurs here. Now, what is reduced, what is oxidized? Neither. Nothing happens here, right? Lead prefers to have all of the electrons, which it does. Aluminum prefers to be in the cation, which it is. So no reaction would occur there. Now, in a few weeks in lab, we're going to actually, instead of doing single displacement reactions with metals, we're going to do single displacement reactions with halogens. But we'll get there when it's time for lab. For now, I have run out of time. So I hope I covered a little bit of everything, but with the other videos that are posted, hopefully there's plenty there to sort of give you a lot of examples as needed. Again, my homework for today is to finish all these worksheets and then scan and post those tomorrow. But any questions for me?